Last meeting, we discussed the concepts of axial stress. And we've gotten these equations. Sigma equals P over A, and then your normal stress and shear stress for inclined planes. Sigma being P over A cosine squared theta, and then for shear stress, again, sigma, or sometimes shear stress will be denoted as tau to denote its shear, equals P over 2A sine 2 theta. So today, let's have some examples. Let's start with number 1. Please prepare your calculators. So number 1, the bar ABCD in the figure consists of 3 cylindrical steel segments with different lengths and cross-sectional areas. Axial loads are applied as shown. Calculate the normal stress in each segment. Once again, normal stress is just P over A. So now we have to know the internal forces P, since A is given. Let's solve. So again, number 1. So what we'll do here is similar to what we did in method of sections, wherein we cut and isolate one of each side, either the left or right hand side. That's the same thing that we'll do here. It's already indicated in the drawings that this is where we'll cut. Okay, let's start here. Now you're gonna cut for every segment so that you can see the internal force for each segment. So we have this, this, and this. Start. So I'm gonna cut here, okay? And then you have a choice of isolating the left or right hand side. Now, obviously, isolating the left side is easier because we're only dealing with one force. Okay, so let's isolate the left side, okay? And then include your external force. And this is equal to 4,000 pounds. So 4,000. Next, make an assumption on the direction of your internal force. For bars like this, direction is only tension or compression. Now, recalling from your MEC 30, these types of structures should be in equilibrium, okay? So even these segments should be in equilibrium as well. So in line with that, since I have a force to the left, to put this in equilibrium, the internal reaction should be to the right, okay? And then let's call that PAB, for internal force for AB. Okay. Do the same thing for the other bars. So here, for bar BC, once again cut, and then you're isolating either the left or right side. In this case, either would be fine. Let's isolate the left. Okay. There. And then again, we have this force, 4,000, and then we have another force. Don't forget that, 9,000. Okay. Next, again, you're gonna assume the direction to put this in equilibrium. Since I have a force to the right that's greater than the force to the left, I need another force to the left to put this in equilibrium. Again, this part is just assumptions. Intelligent guessing. Now this is your PBC. And lastly, for this segment, isolate. Okay, for this segment, obviously it's easier to isolate the right side. Okay, so you're not bound by always isolating the left. So again, you can choose whichever is easier. So you have a force here, 7,000. Once again, to put this in equilibrium, I need another force to the right, and that is your PCB. It's not written, but this should be force point B. Okay, let me just move this. PCB. Okay. Now that we have these are called your free body diagrams. can now create equations for each. So the goal here is to solve for P, because that is what we'll use in the equation sigma equals P over A. To solve for that, we're going to use your equilibrium equations. Recall, equilibrium equations are Fx equals 0, summation of Fy equals 0, and moment equals 0. So obviously, all our forces here are on the horizontal. So this is Fx equals 0. Summation of Fx 0. Sign convention applies. This is to the left. Therefore, negative 4,000 plus, since to the right, P AB equals 0. Therefore, PAB equals 4,000 pounds. And then correct assumptions is positive. It's away from the point, away from your system. Therefore, that's tension. Okay. Next, do the same thing for the other segments. Summation of forces X equals 0. This is to the left, so once again, negative 4,000. This is to the right, therefore positive 9,000. This is to the left, so minus PBC equals 0. Please solve what's PBC. Yeah, it's 5,000. Correct. Trinity and Philip John. Labo meet. Okay, it's 5,000. Positive. Therefore, correct assumption. It's towards your segment. Therefore, this is compression. Okay. And then lastly, for the third segment, once again, Fx equals 0. PCD to the right, therefore positive PCD. 7,000 to the left, so negative 7,000 equals 0. And then PCD is just 7,000. Positive, therefore correct assumption. It's towards your segment. Therefore, compression. Okay, now I have my forces. I can solve for sigma. Sigma AB is just PAB over cross-sectional area AB. Sub in your values, PAB is 4,000. And to get area AB, look at our given. Our area for this segment is 1.2 inch squared. So this is 1. Please solve. What's the answer? Correct. Vanessa and Pauline, or Pau, Stiliore, Barab. .33. And then unit, to find out the unit, our force is in pounds, right? So let's write that, pounds. Tension, pound compression, pound compression. So this is pound divided by inch squared. So pounds per square inch, and we call that PSI. Okay, so that's your stress in the first segment. Do the same thing for the others. Now we have stress BC. P BC over A BC. BC is 5,000. Oh, by the way, don't forget, I forgot, to indicate if it's tension or compression. This is tension. Equals PBC, once again, that's 5,000. The area, look here, it's 1.8. Please solve. What's the answer? Kaya nagkakanood. Correct, Julia and Rick. So Solomon and Diana. Solomon. Okay. Late enrollee. Oh, right. So yes, it's 2. Alright, let's move this. $2,777.78. Unit is PSI as mentioned earlier. And again, compression. And then lastly, sigma CD equals PCD over ACD. PCD 7,000. Let's look at ACD, that's 1.6. What's the answer? Kaya mo ako magtanong. Correct. Pau. Once again, Rika, Soviania, and Pau. Wait for me to ask. Okay. Hintayin yung tanongin ko, what's the answer? Please solve. Late enrollees, yeah, I'll add your name when you get a recitation point for now. Okay, because I'm gonna update it next week since I think there's still late enrollees incoming. Right, it's 4375. 4375 PSI compression. So when dealing with normal forces, please indicate is it tension or compression. Okay, that's number 1. Any questions for number 1? Please answer in the chat. Okay, great. Let's move on to number 2. We have a truss system. Number 2. Okay, let's see. For the truss shown in the figure, calculate the normal stress in members AC and BD. Cross-sectional area of each member is 900 millimeters squared. So we're just looking for stress in specific members. So let's note it was AC and BD, right? BD. Just as a remembrance of what I'm solving for. And then let's also write the given area 100 millimeters squared. So you can either start solving for BD by method of sections or AC by method of joints. So this is where the review comes in, because after figuring out the forces within each member, next step would be to solve for its stress. Okay, let's try starting with this method of joints. To solve for method of joints, I need first this reaction. So that's the first step, solving for the reaction AY. To solve for reaction AY, you're going to take moment about the other support. So moment about H. Okay? So equilibrium equation once again, summation of moment about H should equal 0. Let's start AY, rotate that about H, that's clockwise, therefore positive AY. Perpendicular distance, each panel is 4 meters, so 4, 8, 12, 16. Total distance, 16. Next, this 30 kilonewton. Counterclockwise, so that's negative 30. Perpendicular distance, 4, 8, 12. Next, 70, rotate, again, that's counterclockwise, minus 70. Perpendicular distance, 4. There's no other forces, so equate that to 0. Please solve what's FAY. Correct, Edwin and Audrey. Mira, Manrique. Mira. Okay, 40. Positive 40. Therefore, correct assumption that AY is indeed upward. If you got a negative answer here, that just means your direction was incorrect. It would be downward. Okay. So now that I have that, let's do method of joints. And at A. Okay. We have this. This is 40. That's your AY. Okay. Now again, create intelligent guesses on the direction of your force. This is upward. To put this in equilibrium, I need a downward force, and I'll get that from here. So this is your FAB. Next, I have a force to the left now. I need another force to the right to balance that out. So there to the right, AC. Now create your equations. To solve for FAC, I need to solve for FAB first, right? So to solve for that, let's use summation of forces Y equals 0. Let's start with 40. 40 is upward, therefore positive. Next, FAB is downward, therefore negative FAB. Now, there's no angle given, so we need to figure out its slope. So this is the slope that we're looking for. We have a height that is 3, and then look, each panel is 4. So this is 4, this is 3. Oh, and then, by experience, if you encountered this right triangle a lot of times, you don't even have to solve. That's automatically 5. Your 3, 4, 5 right triangle. Therefore, this is also 3, 4, 5. Okay, now put that into our equation. We're using Fy, so we need the vertical side. So that's 3. So times 3 over hypotenuse 5. There's no other forces that have a vertical component. Equate that to 0. Please solve what's FAB. Correct, it's 66.67. Correct, Trinity and Beatriz Pascual Labo. $66.67. Please store that in your calculator. It should be positive. 66.67. Correct, positive, therefore correct assumption. This is kilonewton, right? Yeah, kilonewton. I assumed it's compression, so compression. Once again, store this. Next. Mhm. Oh. Okay, next, summation of forces X. So let's start once again. FAB to the left, therefore negative. AB, and take the horizontal component. So horizontal side, that's 4 times 4 over hypotenuse 5. And then FAC to the right, so plus FAC. There's no other horizontal force, so equate to 0. Please solve. That's FAC. Considering FAB is 66.67, please use the stored value. Correct, it's 53.33. Correct. Jason and Mamita. La Cruz. Okay, it's 53.33. If you use the stored value, it would be 33. Okay, kilonewton, positive, therefore correct assumption, this is tension. Now that you know its force, you can now solve for its stress. Okay, remember we're looking for stress in FAC. So stress okay, that now we solve for stress. Stress is P over A. So stress AC is PAC over area AC. PAC is, once again, store this. Use the stored value here. So PAC is equal to FAC. That's FAC over area. Area was given 900 millimeters squared. Please solve what's the answer here. Right, it's 59.26. Hmm. So this is kilonewton. Kilonewton divided by millimeter. That's not our normal unit for stress. Recall, our normal unit for stress is Newton per millimeter squared, so that we can convert that to MPa. So instead of FAC, that needs to be FAC times 10 raised to 3 to convert kilonewton to Newton. So that our final answer is in MPa. Okay, so that's 53.33 times 10 raised to 3. Let me write. So that's why you get the answer 59.26. Sorry, 53, 59.26. So Estiliore, VMA, Vergara, Estiliore. And then let's also give it those who solved using kilonewton. 0.059. So Daub, Elaika, and Solomon. Daub, Solomon. No, good job. Oh, oh well. Okay. Oh, ba't ka syntax error? Ano tinype mo? 53.33 times 10 raised to 3 over 900. Baka na times 0 raised to 3. Hindi din. Double check what you typed in your calculator. Baka na-divide by 0 mo. That's gonna give math error. It's 59.26. And then unit, okay. Unit, once again, this is now Newton. This is millimeter squared. So Newton per millimeter squared. And this simplifies to MPa. Okay? So take note of our conversions, MPa, kPa, GPa, right? So that is for AC. Now let's move on to BD. And again, for BD, we're going to use method of sections. So it's already shown here. Where did that come from? It's already shown here. BD. We have this cut. So now it's a matter of isolating left or right hand side. For the left side, I've already solved for AY, so it's much more convenient to isolate the left side. So let's do that. Okay. Okay, this is method of sections. Right. So in method of sections, recall we have these forces. Okay. And then, as I've mentioned before, hindi napindot yung pen. Okay. Okay. This is not my screen, okay. Anyway, moving back. Recall that I'm used to putting all of these forces for method of sections in tension. That's why this is how I draw it. Okay. And then note the forces, the internal forces that it will show. So FBD, BE, and CE. BD, BE, and CE. Now the only force that I want is BD. Okay? So to solve for that, you need to find out a point where the other two unknown forces will intersect. Can anybody give me where that point is? Where the other unknown forces will intersect, namely BE and CE. Yeah, very good. Tim, and Beatrice. So Mondragon, Pascual. There. It's at E. E. So even though it's not shown here in your method of sections drawing, you can still use point E, which is outside that drawing. Okay, it's still allowed. So if I extend that, right, we have this E. Okay, so let's take a moment about E. Let's start with AY. Rotate AY about E, that's clockwise, therefore positive AY. Perpendicular distance, this is 4 as well. So that's 8. Next, 30, rotate that about E, that's counterclockwise, so negative 30. By the way, this AY is actually 40. So I can just write that immediately. So 40 times 8 minus 30. Perpendicular distance to E, that's 4. C to E, that's 4 meters. What else? BE and CE passes through E, so I can just ignore both of those forces. So we're left with BD. Rotate BD about E. That's clockwise, so positive FBD. Perpendicular distance is this, okay, right? That's equal to 3. So FBD times 3. No more forces, equate that to 0. Please solve what's FBD. Very good, it's negative 66.67. Please include positive. So positive, there's no sign, or negative. So please indicate if it's negative or not. So very good, Tim and BMA. Mondragon, Bergat. No, not BMA. Mondragon and Sierra. Sierra. So Gutierrez, Mondragon. Okay. Mondragon. Okay. It's negative 66.67. Therefore, for incorrect assumption, this is actually 66.67 kilonewton. I assume tension, that's incorrect, so it should be compression. Should also complete answer. This is tension. Okay. Next. Okay, now that I have my force BD, I can solve for stress BD. Stress BD is PBD over area BD. FBD is just 66.67. Once again, convert kilonewton to newtons times 10 raised to 3 over area, which is 900. Please solve what's the answer. Like what we did earlier, you should also store this and use the stored value for your answer. You have it correct. Correct, Vanessa. Castiglione and Michela. Castiglione. Oh man, so simple. Miguel Gian, late enrollee. Mhm. Who else? Beatrice. Pascual. 2 points ka na din. Yan. Francine Colera. Rolling and rolling. Yan. It's 74.07. If you use the stored value of this, not 0.8, so 0.7. Again, Newton per millimeter squared or MPa, and then it's in compression. Compressive stress. And that's your final answer. Okay? That's number 2. Okay. That's number 2. Any questions for number 2? Please answer in the chat. Yeah, no, don't round off. Use the store function of your calculator. You're only gonna round off at the last, your final answer. Okay? So memorize or learn the store function of your calculator. Okay, no questions. Let's move on to number 3. Number 3. The figure shows a 2-member truss supporting a block of weight W. Cross-sectional areas of the members are 800 millimeters squared for AB and 400 millimeters squared for AC. Determine the maximum saved value of W if the working stresses are 110 MPa for AB and 120 MPa for AC. Okay, so previously we've solved for stresses. Now we're solving for maximum force allowable based on the given allowable stresses or working stresses. Okay, so the solution to this is a bit different from what we solved so far. First step, write out your given. Cross-sectional area 800 and 400, and then working stresses 110 and 120. So let's write that down. Okay. So cross-sectional area of AB was 800 millimeters squared. Cross-sectional area of AC is 400 millimeters squared. And then we have working stresses for AB, 110 MPa. And then for AC, it's 120. That's our given. Now, some of you might think the solution of this would be taking this, know that stress is P over A. Therefore, PAB is 110 times 800. Okay, and after knowing PAB, do the same for PAC, you'll get a value. Then from that value, you're gonna do free body diagram here, summation of forces, right? And then you're gonna use this to solve for W. That is incorrect. Okay. Because what we're doing here is you're assuming bar AB and bar AC are working independently. Okay? That is not the case. These two share the load of W. Okay? So we should solve it that way. So that means we need an equation for AB, relating AB, AC, and W. So that's the first step, not this. So we're going to ignore this for now. Because again, first step, create an equation relating your variables. Because these two forces share this load. Let's do that. Once again, as I've said earlier, using equilibrium equation, summation of forces. Let's start with summation of force X. We may start with force Y, doesn't make a difference. So Fx equals 0. Let's start with this. This is in tension, so I like calling that P. Tension AB. Okay, it's to the left, therefore negative. And then we are given angles from the x-axis. So the x component of this is F cosine theta. So PAB cosine 40. Next, how about this TAC to the right? So positive TAC cosine 60. By the way, if to make things clearer, if we try drawing this free body diagram, okay, let's try that. Okay. Drawing the free body diagram, you get something like this. So you have this point, weight downward always. Then once again, whenever you have cords, ropes, lines, in this case, we have a member supporting weight. It's in tension. It's up. So let's call this TAC, TAB. You may still use force F, P, doesn't matter. Okay, this is just my preference. Then take note of the angles. This is 60. This is 40. That is how I came up with this equation. Okay, so to the left, therefore negative. To the right, therefore positive. There's no other horizontal forces, so equate that to 0. As you can see, there's nothing to solve for here yet. So we'll let that be. We'll move on to the next equation, which is summation of forces y equals 0. So summation of Fy equals 0. Let's start with AB again, upward, therefore positive. PAB sine 40. Next, TAC upward, so positive TAC sine 60. We have weight here downward, so minus weight equals 0. Okay, nothing to solve for there again. But my reminder, what we're looking for is just an equation relating all these three variables, which we have right now. Now I just need an equation relating only either TAB and weight or TAC and weight. Okay, because from that, I can solve for weight. So in order to do that, we'll just manipulate our equations. Once again, I need an equation relating TAC and weight, and then another equation relating TAB and weight. So let's take this. Let's call that equation 1. And then this is equation 2. So from equation 1, okay, I'm going to create another equation for TAB. So I'll transpose TAB to the other side and divide both sides by cosine 40. You'll get TAB equals TAC cosine 60 over cosine 40. Okay. Then, let's call that equation 3. And then we're going to sub this in equation 2. So for equation 2, subbing TAB here, you get TAC cosine 60 over cosine 40 multiplied by sine 40 plus TAC sine 60 minus W equals 0. And as you can see, the only variables here now are TAC and W. Now let's simplify. Factor out TAC. So TAC times cosine 60 sine 40 over cosine 40 plus sine 60. Then transpose W to the other side, you'll get positive W. And then from this, you can finally create the relationship between AC and W. Please solve what is this equal to, then 1 divided by that to get the coefficient of W. Okay. Okay, very good. It's 0.7779. Manriquez. So Edwin and Audrey, very good. Mira and Manrique. Okay. It's 0.7779 W or 0.78. However, we store this. Okay? Yeah. And then do the same thing. Now I need an equation for TAB in terms of W. So we'll use equation 3. Equation 3. Okay. TAB equals TAC is 0.78 W. Right? Cosine 60 over cosine 40. Please simplify. What's the stored value? 0.78 times cosine 60 times cosine 40. Correct. It's 0.51. Correct. Laika and Julia and Jonelle. So now, Julia, I think you already have 2 points. Yep. So now, and then 1, Jonelle, wrong. 0.51. And once again, please store that because this is a lot of decimal places. Okay. Now, what are we going to do with this information? So now, this is where you can use your stress, okay, the given stresses. So let's start with AB. Okay. AB. So AB, stress equals P over A. This is AB, 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 stress AB. What's stress AB? 110. Copy that. 110 equals, now PAB is the same as your TAB. And that's 0.51 weight. So copy 0.51. Again, please use the stored value of this weight over area. Area of A is also given 800. Make sure your units are uniform. How? Recall, okay? This is MPa, Newton per millimeter squared. Area is millimeter squared. So yes, they're consistent. They're both millimeter squared. And then the unit that you'll have for force is Newton. Please solve. What's W? Okay. Correct. So Ruel and Wells. Correct. Well, Audrey and Ronald. Audrey, I think you already have 2 points. So, well, makatangal. Ayan. Oh, like, ano, yeah. Daming late. And one, correct. It's 172, 172,549.02 newtons, or 173 kilonewtons. Okay, or you can just write it this way as well. Okay, it's 1.73 times 10 raised to 5 newtons, or, okay, depending on what's being asked, what unit is being asked, it's also 172.55 kilonewtons, or 173 kilonewtons. Okay, so that's only the allowed weight considering stress AB. Okay, now we have to check as well for stress AC. We'll do the same thing. Stress AC equals PAC over area AC. What's stress AC? 120 and area is 400. 120 over, nope, 120 for stress PAC. Let's look at the equation. 0.78, once again, use the stored value. 0.78 W over area, which is 400. Please solve what's W here. Okay, correct. Jason and Sierra. De la Cruz Gutierrez. It's 61,538.46 newtons, or 61.53 kilonewtons. Okay, or so again, you can just write it this way. 6.15, 6.17. Here's the stored value. Okay. Let me check. No, 6.17. If you use the stored value, you should get 6.17, not 15. So 6.17 times 10 raised to 4 newtons. Okay. So we have this problem now. Which of the two should be our answer? Let's look back at our question. Determine the maximum safe value of W if the working stresses are given. So what we solved for are the allowable weight for each member. This is the allowable weight for member AB. This is the allowable weight for member AC. So as a whole, what is our maximum safe value? Anyone? Is it AB or AC? Let me know. AB or AC? So again, answer AB or AC. Everyone, please answer so I know the majority answer. Again, everyone, please answer. Ganang hahabol? Okay. Maximum safe value. Theories. The correct answer is AC. It's 6.17 times 10 raised to 4 Newton, or 61.71 kilonewton. Why? This is the safe value. This is the maximum allowable value. This structure, the complete structure, can carry. Why? If I use this, remember that's times 10 raised to 5, okay? If I use that, this is greater than this. This is the only this is the maximum allowable for AC. If I choose this, AC will collapse. Why? Because this is greater than what's allowable for AC. So the structure will fail because AC fails. Okay? So that's how you'll determine what's the maximum safe value. Or in short, if we're looking for maximum force allowed, always choose the least value. So here it's this, times 10 raised to 4. Okay? So that's the way to determine which of the answers should we get. Okay? So this is option 1, option 2. Okay? Once again, there's a maximum safe value, allowable force, maximum allowable force. That is the least value, the smallest value. Because anything higher than that will cause that structure to fail. So again here, this force will cause this to fail, or will cause this to fail. Because this is the maximum. Alright? And that's number 3. Any questions for number 3? Please answer in the chat. Okay, good. Let's move on to number 2. The following questions are a bit easier. So let's skim right through it. Number 4. The rectangular wood panel is formed by gluing together two boards along the 30-degree seam as shown in the figure. Determine the largest actual force P that can be carried safely by the panel if the working stress for wood is 1120 psi. Normal and shear stresses in the glue are limited to 700 psi and 450 psi respectively. So this is an example of why we solved for the normal and shear stress for inclined planes. Okay? Here, that was the importance because structures like wood are glued together diagonally. That's why you have an inclined plane. That's why these equations were important for that situation. Okay, going back. So the question here is the same as number 3. We're looking for maximum force P allowed given the following stresses. So once again, first step, write the stresses or write the given. So first, theta is given 30. So you can also write that theta is 30. What else? Stress. I'll call it stress W, normal stress W for wood. Okay, and that was 1120 psi. What else? We also had stresses for glue. Okay, working stress for wood 120. Stresses in the glue. So let's write that. Let's call sigma G for normal stress for wood. That was 700. And then shear stress for glue. We can also use G again. But remember, I said earlier, another symbol for shear is tau. So I'll use tau. Tau for glue, G for glue, is 450 psi. So to solve, we'll do it this way. We're gonna test each material. So previously, right, we created an equation relating the two possible forces, one for AB, one for AC. Now, luckily for this, there's only one force, it's just P. So I don't have to go through that anymore. That force P is what we'll use in our equation directly, okay? Once again, the only force here is P, so no need to go through what we did earlier. Okay, so let's test. Let's test first for wood, since that's the easiest. Normal stress for the wood. Okay, so sigma W for wood equals P. Since P is the same whether for wood or glue, so that's just P over cross-sectional area for wood. Plug in our values. This is 1120 equals P over A. Now let's find out what's the area of A. What's the area of that wood? The area is just this. Okay, that's the cross-sectional area of your wood. As you can see, this length is equal to 4, this height is equal to 1. So area is just 4 times 1. Solve for P, what's the answer? Correct, it's 4480. So correct, Sierra. I think I already have 2 points. So Muni, Miguela, and Jay. Muni, Muni. It's 4480. And unit, we're using PSI. Oh, by the way, you have to make sure your units are consistent. Stress is PSI, that's pounds per square inch. Our area is also in square inch, right? Inch times inch. Therefore, this unit is pounds. Okay. All right. Okay, so that's another thing to consider. Make sure your units are consistent. So inches will cancel out. This is pounds. So that's not the answer yet. So again, that is one option. Now that we're done with wood, let's move on to the glue. And luckily, we have equations for that. Okay, so let's go back to our equations. The normal stress for wood, normal stress for an inclined plane, which is where our wood is, where our glue is P over A cosine squared alpha. Okay. So P over A cosine squared theta. Sigma G is 700. PSI, pounds per square inch. P is what we're looking for. Area, again, capital A is the cross-sectional area of your object, in this case wood. So that's still 4 times 1. And then cosine squared theta. This theta is the angle from the horizontal to the incline, and that's given as 30. So cosine squared 30. From this, please solve what's P. Correct, Aaron. And Janelle. Mendoza Flores. Aaron, wait, and Roly. Mm-hmm. Mendoza. Okay. 1. 3733.33. Once again, the unit of that is pounds. Again, that's another option. Next, let's look at the shear stress. Equation for shear stress is P over 2A sine 2 theta. We use the symbol for shear stress as tau. Tau G P over 2A sine 2 theta. Sine 2 theta. Plug in our values. Tau is 450 psi still, so no problem with our units. P times 2. Area, again, capital A is the cross-sectional area of your object. So that's still 4 times 1. And then sine theta is 30. So 30. Please solve what's P. Wala pang points dyan. Recite. Okay, so correct. Miguela and Ronel. So Juano and Muni. And Aaron. Juano, Muni, and Juano. Juano. And 2 is already 2. So let's give it to Aaron. It's 4156.92. Now, the question is, which of these three is the answer to our question, which is, let's go back what is being asked. Largest axial force P that can be carried safely. So which of the three should be our answer? Is it 1, 2, 3? What's your answer? 1, 2, or 3? Which is the final answer? Once again, everyone please answer so I can decide what's the majority. Just choose between 1, 2, and 3. Okay, correct answer is, okay, most of you got it correct. It's 2. It's this one. Why? It's the least answer. It's the minimum value. Although we're looking for largest actual force, it's also the one that's safely carried. Okay? So 3, 7, 3, 3, 33 pounds. Why? Again, let's say if we use force 4,480 here, that's greater than what the glue can carry. So the glue will fail. So I can't use this. Okay? Anything higher than this, the glue will fail. We don't want a part of our structure to fail. That's why this is your answer. Okay? That's number 4. Any questions for number 4? Okay, great. Next. That's 5. Number 5. So numbers 5 and 6, I'm just gonna answer since we're almost out of time and I want to finish this lecture so that we can move on to a new lecture next meeting. Okay, so again, you may just listen. I'm not gonna take recitation anymore. Number 5, a hollow steel tube with an inside diameter of 100 millimeter must carry a tensile load of 400 kilonewton. Determine the outside diameter of the tube if the stress is limited to 120 meganewton per meter squared. So basically, we have a hollow tube with an inside diameter given and a tensile load. So we need to know what should be its dimension, specifically outside diameter, so that it won't exceed your stress 120 meganewton per meter squared. Since again, that's your limit, stress limit. All right, first step, write your given. First, we have an inside diameter. So let's call that DI. And that is, I believe, 100 millimeters. Okay, another thing that we have is your tensile force. So you can call that T for tension or just P. It's the same thing. So 40 kilonewton. It's in tensile force, so let's call that tension for P. And then we have limit or stress 120 meganewton per millimeter squared. And that actually is also equal to MPa. So this is also 120 MPa. Okay? So Newton per millimeter squared and meganewton per meter squared rather. Meter squared is also MPa. Okay, so we're looking for DO. So your steel tube looks something like this, okay? So we're gonna use the equation P over A, and your A is this cross-sectional area. Okay, so it's this. Okay, so therefore, we'll use this equation. Okay, our stress is 120 Newton per millimeter squared. So this is your P. This is what we're looking for. Sorry, this P is given 40 kilonewton. MPa is also Newton per millimeter squared. Recall, I told you to make sure your units are uniform. This is MPa, so I need my force to be in Newton. Okay, so I'm going to convert that 40 to Newton, so times 10 raised to 3. Okay, and then over area. This is your area. It's a ring, and recall the area of a ring, that's just pi outer circle minus inner circle. So pi over 4d squared for outer diameter for first, and minus this empty space, which is again area of a circle, pi over 4 d squared. DI is 100 millimeters, uniform, so I can use that. No need to convert. Okay, and this is our working equation. And then from this, I can solve for DO. Okay, so therefore, DO is 119.35 millimeters. Okay, so it's basic. It's just P over A. Where A is not given, you have to solve for it. That's number 5. Next, let's move on to number 6. Homogeneous 800 kilogram bar AB is supported at either end by cable as shown. Calculate the smallest area of each cable if the stress is not to exceed 90 MPa in bronze and 120 MPa in steel. So this looks familiar, right? We're again looking for an area dimension. And then we're given your working stresses, 90 for bronze, 120 for steel. So the way to go about this is similar to the first one we encountered, wherein we need to create an equation involving the given forces or the unknown forces. Okay, so first let's try to create a free body diagram for this. So you have this straight bar. It has a weight of 800 kilograms. To make that force, we need to multiply this by 9.81, okay, to make it weight. And that is at the middle. So this is 5, this is 5. Next, we have these rods, and these rods put this system into equilibrium. So most likely, they're upward, okay? So let's call this force in bronze, member. Force in steel member. So now you have your free body diagram. And then you can say by symmetry, okay, this is symmetrical, right? 5, PBR is actually equal to PST. Okay? And to solve for that, okay, since this is symmetrical, these two forces will share this load equally. So that means that's 800 times 9.81 over 2. And the answer to that is 3924 newtons. Okay, since this creates a weight in newtons, kilogram meter per second squared. Okay? Or you can solve, we can take moment about this point, you can solve for PBR, and then summation of forces y, you can solve for PST. Okay, you can do that as well if you're not confident it's symmetrical. Now that I can solve for area using the given stresses. Okay, let's write the given, I didn't write it. Stress for bronze was 90 MPa. Okay, once again, this is given. Stress for steel was 120 MPa. Okay, I'm gonna use these two to figure out what's the allowable area. Okay, and then luckily, PBR equals PST, so that's easier to solve. So stress BR equals PBR over ABR. Okay, so 90 equals 3924. Are we looking for area or diameter? Area, okay, so just A. 3924 over A. Solving for A here, A of bronze, you get 43.6 millimeters. Now, what's the unit? So the unit that we've been using, this is, once again, Newton per millimeter squared. This force is in Newton. So uniform units didn't need to convert. We're going to be left with millimeters squared. Okay. Do the same thing for steel. PST over AST. This is 120. PST again is same, 3924 over AST. So from this, we can solve for AST, which is 32.7 unit millimeter squared. Now, you might think I have to choose which of the two. No, we're not looking for smallest area possible for both portions. No, we're looking for smallest area of each cable. So each cable, meaning both are answers. This is the smallest area possible for the bronze rod. This is the smallest area possible for the steel rod. Okay? We're not looking for smallest area for both rods. It's for each. That's our answer. Okay, that's numbers 5 and 6. Do you have any questions? Once again, please answer in the chat. Okay, so that ends our topic for axial stress. Before I dismiss you, we have a few announcements. On Thursday, we'll have new discussion, shear and bearing stress. I've already uploaded your lecture. Okay, let me show you. Now, for those who are late enrollees, if you haven't read the announcement yet, okay, please do. So I'll show it to you anyway. It starts slowly. Look for the announcement. Please read that. For late enrollees. So watch the Zoom recording. Yeah, you can watch it here. I've been uploading that. Especially this, watch the orientation and course introduction because some of your questions might have been answered there already. So watch that and read this. Okay? So watch and read so that you can get caught up in our lecture. Also, we had a diagnostic exam last Saturday. You can find it in week 1. And hard deadline, June 5, 4:30 p.m. So you may answer your diagnostic exam until Saturday, 4:30 p.m. You need to send me an excuse letter so that I can consider your score. Details are in the Zoom recording. But once again, you need to send an explanation letter by your parent or guardian, signed by your parent or guardian with their ID, photocopy of their ID, right? You don't have to ask me when you can take the diagnostic exam. You can just answer it immediately within the week. You just have to send me this excuse letter, okay? And just follow the format for the subject for the course message of this. Once again, just read and watch the Zoom recording. Paano pag nakasabay naman po sa pagsagot? No problem. I'll still consider your score. I think your score is already shown if you submitted within the time frame. Okay. Yeah, no problem then. Any other concerns and questions? None? Okay. Wala na ha? Wala nang habol. Okay. Since you don't have any more questions, you may go. Goodbye, class.
Okay, ma'am.
Bye, ma'am.
Thank you, ma'am.
Thank you po,
Thank you,
ma'am.
ma'am.
Thank
Thank you
you.
po.